ME 347, Example 18. Water is pumped at a volumetric flow rate of 30 liters per second through a centrifugal pump operating at a speed of 1200 revolutions per minute. The impeller has the dimensions indicated in the table. For part A, calculate the inlet blade angle for which the inlet velocity has no theta component. For part B, draw the inlet and outlet velocity diagrams to scale. For part C, calculate the ideal head. Finally, for part D, calculate the mechanical power needed to turn the pump shaft. For this problem, we will assume steady, one-dimensional flow through the blades of an Newtonian fluid with constant properties, which is water at standard temperature and pressure. We will also assume negligible torque due to surface forces, in particular friction, with respect to the large shaft torque, and that the mass is balanced. Finally, based on the problem statement for part A, we will assume swirl-free flow at the inlet. For part A, calculate the inlet blade angle for which the inlet velocity has no theta component. This is called swirl-free entry. From a vector analysis, the theta component of the fluid velocity is shown. Setting this equation equal to 0, we get an equation to solve for the inlet blade angle that depends on the volumetric flow rate, blade velocity, and the inlet flow area. First, we convert the impeller speed to radians per second, and then use this value to calculate the blade velocity at the inlet to be 12.6 meters per second. Note that this is also the fluid velocity due to the no-slip condition. Second, we calculate the inlet area using the impeller radius and blade height. Substituting in these values and our volumetric flow rate, we get an inlet blade angle of 20.8 degrees. For part B, we will plot the inlet and outlet velocity diagrams to scale, which requires calculating all of the fluid velocity components. For the inlet, for swirl-free entry, the theta component is 0. Also, we have already calculated the blade velocity. For the radial component, from conservation of mass, we calculate a velocity of 4.77 meters per second. Finally, for the fluid velocity component, tangent to the blade, again from vector analysis, we get a velocity of 13.4 meters per second. We continue by now repeating all of the velocity calculations from part A for the flow at the outlet. In addition, we now also need to calculate the theta component of velocity for the specified blade angle at the exit. Finally, we use these results for the inlet and the outlet to make velocity diagrams, which are plotted using MATLAB. Note that for these figures, the radial velocity component is plotted on the y-axis versus the theta component on the x-axis. Also, the fluid velocity vector v is the vector sum of the blade velocity u and the fluid velocity tangent to the blade w. At the inlet, for swirl-free entry, the fluid velocity is in the radial direction only. After moving through the blades, the fluid velocity turns almost completely towards the theta direction at the outlet. This results in the desired change in angular momentum for the fluid moving through the blades. For part C, calculate the ideal head. The equation given for the ideal head is derived by assuming ideal flow through the blades, as specified earlier in the assumptions, and applying an angular momentum balance combined with conservation of mass to a control volume containing the fluid. The resulting equation is further simplified for swirl-free entry to obtain the relation given. Substituting in our values for this problem, we get an ideal head of 50.3 meters, which corresponds to a large pump. This means that under ideal conditions, this pump would be able to pump water upwards by about 50 meters. For anything higher than 50 meters, there would be no flow. Under actual conditions, due to inefficiencies, we would expect the actual limit to be lower based on the details of the pump design. For part D, calculate the mechanical power needed to turn the shaft to produce the ideal head given in part C. For this calculation, we will assume that the mechanical head is equal to the ideal swirl-free head. This implies that there are no losses between the torque supplied to the shaft and the power delivered to the fluid. Based on this assumption, we plug in our values to the equation used to convert from head to power to get 14.8 kilowatts, which is again large and is consistent with the large head that this pump is ideally producing.